So, welcome back to the class. So, in the last class what we discussed was solving the Laplacian equation for T x y, right, and where the temperature was specified along the boundaries, along the 4 boundaries, and on a plate we had specified the temperature, and we solved self consistently for the points inside the plate, leaving out the boundaries, and we found the final temperature of the system. Right, there was no time dependence. We had said in the diffusion equation del phi del t was put to 0. We are just looking at the steady state solution. Now, when you specify the boundary conditions and you specify the temperature, which is the quantity we are solving for at the boundaries, it is called the Dirichlet boundary condition. Right. So, it is a name when you specify t as a function or phi or whatever quantity you are solving for at the boundaries. On the other hand, you can also specify the dt dx, the dt dx at the boundaries, or dt dy along the boundaries, which is the first derivative of the field that you are solving for. In our case, it was temperature. And when you specify dt dx or dt dy along the boundaries, then you call it the Neumann boundary condition. Now, why or what does it mean by specifying dt dx or the gradient, the first derivative of the field we are solving for dt dx or dt dy at the boundaries? What does Neumann boundary condition imply? In our case, it would imply that we are actually specifying the heat current. And why is that? Let me remind you about the Fourier's law, which we had discussed in the last class, and q vector was the heat current, and that was proportional to kappa, the thermal conductivity, the gradient of temperature, and that is the so called Fourier's law, from which we obtained the so called diffusion equation for heat transport in a plate. Right, and basically, of course, so if you specify this and you say that okay, I specify how much amount of heat is transported at different points in x and y along the boundaries, right, which means that you are essentially specifying. So, there was an error here, it should be like this. So, if you specify the basically temperature gradient only at the boundaries, when it is reached steady state, you are basically specifying the so called Neumann boundary condition. So, q x, right, if you specify q x, which is basically kappa dt dx, right. So, how much of heat is being transported on the left side of the box along the x direction. So, if you specify this quantity, the heat current along the x direction, you can specify that, and then you can also specify the heat current along the y direction at the appropriate boundaries. And then the question is, how would you solve for the Laplacian with the appropriate boundary conditions and get your heat or temperature profile as a function of x and y, and that is what we are going to discuss today. So, just to summarize, if we specify instead of T x y at the boundaries, we specify the heat flowing in per unit time per unit area at the boundaries, and we specify suppose q x equal to a 0, some amount of heat being transported along the boundaries, and q y equal to some value c 0 say along the boundaries. How do we solve the Laplacian and get our temperature profile? So, that is what we are going to discuss today. Having said that, and before we come down to actually solving a Laplacian with Neumann boundary conditions, let me also tell you that you can also have Cauchy boundary conditions. And in the Cauchy boundary conditions, you specify both T, the temperature as a function of x and y only at the boundaries, as well as the gradient dt dx along the boundaries, right, and you can specify it along x equal to 1 or x equal to Lx and so on and so forth. And you can also specify boundary conditions where the both are specified. This is a more restrictive system, it is a bit more complicated. We are not going to discuss this, but just for your information, you can also specify boundary conditions like this, and you might have when you solve partial differential equations in a real case have to handle such systems, and then you have to look up the book and learn how to do it, right. Okay, coming back to our Neumann boundary condition, where we are specifying del t del x at the boundaries. Just to remind you that as per the second order scheme of Taylor expansion, where such a you basically use such a expression for dt dx. Just to tell you that though we have not discussed the second order scheme in great detail, we have not discussed it at all for that matter, it is there in the books. You can have also first order schemes in the Taylor expansion, and then you can write dt dx equal to T temperature at x plus delta x minus T at x by delta x, and this is the so called first order scheme, right. But the expression we are using for del 2 T del x 2, this is already the second order scheme. So, for consistency I am writing down the expressions of dt dx in this form, which is the second order scheme. If you want to know more about it, open a book, you will get the derivations and so on and so forth, and it is obtained through Taylor expansion, right. So, you can refer to this book if you want to know more about first order expansion, second order expansions, stability. When you mix up terms with first order expansions like this with second order expansions for the suppose the second derivative d2 T del x 2, there are certain stability conditions to be maintained, to be checked for. So, we are not going that, we are just choosing a second order scheme method, this second order method formula, and dt dx can be written like this, which essentially when you write it in the discrete manner, it is T I plus 1 delta x is I plus 1 j minus T I minus 1 corresponding to x minus delta x j by 2 delta x, and similarly dt del dt dy can be written as T I j plus 1. So, basically what is the value of the temperature in the y direction, one lattice coordinate up and one lattice coordinate down divided by 2 delta y. So, this is what we have to so this is what is essentially specified. So, when you specify Neumann boundary condition, you are specifying del t del x at the boundaries, which will have some values, and that in turn can be written by these formulas, right, the finite difference method. But now you have a problem, and let me tell you what the problem is as well as the solution, of course. So, your Laplacian, right, as we discussed in the last class, can be written in this expression, which stands for basically del 2 T del x 2 and del 2 T del y 2 can be written like this, and that is equal to 0, and this is the equation we have to solve for over the entire lattice. Now, if this is your lattice, right, previously the values of the temperature was specified at the boundaries at these points, say, and these points. So, we were not, they were fixed at the boundaries, the value of temperature was fixed at the boundaries. As a consequence, we were not changing or updating the value of the temperature at these boundaries, because they were considered to remain fixed, and we were only updating and finding out the steady state temperature of the points within the lattice. We were basically solving for those iteratively, but in this case, but in today's class, what we are discussing is what is specified is not the temperature, but the heat, right, at suppose this boundary, and what is the heat being flowing in or out at this boundary, and what is the heat flowing in or out at this boundary, and this is the last boundary, right. So, the temperatures at these points can change and they can be updated. So, that so you are specifying the amount of heat input and heat output along the boundaries, and the temperature will evolve as per the solution of the Laplacian equation given the certain boundary conditions, and you are solving exactly for that. So, what is specified is at each point here, here and here and here, what are the values of current, heat current coming in. The simplest case will be the heat coming in would be uniform along this boundary, and the heat going out would be uniform along this boundary. But in principle, you can also have different amounts of heat coming in here and here and here. So, basically A, which is the measure of the heat coming in the boundary condition, right, dTx del T del x, it can have different values as a function of y, the j coordinate. It can have different values along this, right. Though in our test case we will consider that the values of A are independent of j, but you can have different amount of heat as you go here, you can have different amounts of heat leaking out as you go from here to here, you can have different amounts of heat leaking out here to here. Basically, that would correspond to different surface properties, you can treat the surface differently. So, that is what we are specifying, and the more important thing is we have to find out the values of the temperature for these points as well. Now, when you write down such an expression when I equal to 1, right. So, if this is your I equal to 1 at this point for a particular value of j, suppose for this point or this point, then you also have I minus 1, I minus 1. So, if I is 1, I minus 1 is 0. But you do not have those points on the lattice, right. You have to solve for you need the values of this point which is outside the lattice, but you do not know what is T I minus 1 j. Similarly, if you were writing for j equal to 1, say suppose this point or suppose this point, right, when j equal to L y. So, when j equal to L y, you would have j plus 1, which is outside the lattice, right. If j is L y and j plus 1 would be outside the lattice, and then how do the question is how do we solve for this, right. And the solution is, so you have to write down the expressions. So, to solve for T I j, you need the values such as you need the values of this and you need the values of this and so on so forth, especially if they are the boundaries, and the way you solve it is discussed in the next slide. Here we ask you to note that Aj is that heat current, right. So, Aj is this heat current, that is what you are specifying, del T del x is what you are specifying along the boundaries instead of temperature. So, this Aj equal to del T del x at x equal to 1 and y equal to j can be written as T 2 j minus T 0 j by 2 del x. 2 0 j is essentially these points outside the lattice which do not exist, and the question is how do you figure out this value. And the way you figure out this value is by noting that if Aj which is specified, then you can write this equality Aj equal to this, and then what you have is you solve for T 0 j. You basically you solve. So, you have this equation, get delta x on the other side of the equation, that is what I have done here, and write T 0 j in terms of A j for each value of j. right. And similarly, suppose you have specified the heat current along suppose y equal to L y, right. So, suppose you have for different values of I, you have specified the heat current at basically y equal to L y. That in turn can be written just like this in a similar expression where d I is nothing but this, right. So, basically this L y plus 1 here, right, L y plus 1, and L y plus 1 is essentially these points, which again those exist, those are ghost points, right. So, basically what you do is write this quantity by a similar algebraic thing in terms of d I, right. So, you basically write the temperature here in terms of d I by this algebraic formula. So, you can do similar things for all the ghost points which are here, which will be b j, b 1, b 2, b 3, b j, and you can similarly write the temperatures for these ghost points which do not exist, but will be there in the expression for the Laplacian in terms of C 1 and then C 2 and C 3 and in general C I, right. So, finally, let us focus at the Laplacian at this point, and on this boundary the Laplacian which you have, the expression is this, right. You have this expression and you have T 0 j here if you wanted to solve for T 1 j, if you wanted to solve for T 1 j you have T 0 j sitting here, right, and this part is standard, you do not have to worry, it is basically the temperatures on the neighboring points along the y direction, but this T 0 j is now substituted by this expression which we figured out here. So, I have just substituted that expression here in lieu of this, and now what you have is all the quantities whose values you know. I mean, at least you know at a particular iteration, and of course, iteratively the values of each of these points shall evolve, and when its value does not change while maintaining the boundary conditions now in terms of dt dx, or rather in terms of A j, then they basically become stationary, means they do not evolve within your tolerance factor, you say that you have got your answer. But at least you at your 0th iteration and your 1th and 2nd and whatever nth iteration, for each case you have the values of all these quantities, right. So, now you solve for basically T 1 j along the boundaries. T 1 j is the temperature at this point and this point for different values of j, for different values of j along the y axis, right. So, j is varying for each value of j, you find out the temperature at the boundary, and the formula by just doing some algebraic manipulation of this, you basically get this, right. So, what I have done is basically multiply by del x square the whole square and just separation of variables, and basically now T 1 j depends upon all the neighboring points, and the boundary condition is sitting here nicely, right. From here it is sitting nicely here. So, you have applied the boundary condition, right, and if delta x equal to delta y, just as previously the expression reduces to even a simpler expression like this for all j, and of course, A j has to be specified, that is what you are specifying, dt dx is what you are specifying for at the boundaries for each value of j, and then all that you need is solve such a simple equation. Now, for the other boundaries, for the boundaries along this and this and this, you can similarly write down expressions which are written here for x equal to L x for different values of j, which is essentially this boundary x equal to L x, right, and different values of j, that can be written in terms of doing a very similar procedure as was discussed in the last slide. The expression can be this, and note that del t del x at x equal to L x, which is b j, it is setting nicely here, right. So, it is basically so you have used similar expressions, there is a setting there. Similarly, along the other boundaries, what you have specified is d 1, d 2, d 3 along this boundary, and c 1, c 2, c 3 along this boundary. As you change x, right, and at each point you could have different amounts of heat coming in at different points of I. You have this expression where you see that C I is sitting here, and note delta x equal to delta y, the value of delta x is also sitting here basically, right. So, you get these expressions, and similarly for the other boundary you have this expression where you have d I, and note delta x equal to del y, and that is why we have this 1 by 4 factor, and these are all terms which you have access to. However, there is still a complication, and what is that complication? Note at these 4 corner points, heat is coming in, our boundary conditions are specified, del t del x A1 is also specified, del t del y C1 is also specified. Similarly, for here, right, C L x is specified as well as B 1 is specified. So, you have basically heat going out from this direction as well as heat going out from this direction, and so on so forth. For that, you have to work a bit more in terms of working out the algebra, but what I have done here is written down the expressions of how to calculate for T 11, T 1 L y, T L x 1, those are the 4 corners, and T L x L x. So, these are of course for all the cases when delta x equal to delta y, it is a bit more of algebra, but these are the expressions which is basically a few steps ahead from doing this, right. So, what do you have? So, just to figure out where we stand, you had to solve the Laplacian at the boundary, where boundary conditions were given, where the heat current del t del x was given, that you have used such an expression to get rid of the expressions in the Laplacian which was depending upon these host positions, those you have replaced in terms of A j and d j and c j and b j. So, basically you have these now in the expression for the update at the boundaries, right. And what we shall consider is look at a simple problem where the AJs across for all values of y is minus 700, for all values of along this boundary is 100, and along this boundary is 200. So, basically heat is coming in here, and basically the B j is 400. So, heat is going out from here, heat is going out from here, but the amount of heat going out from here and from this boundary C j equal to 200, which is more than 100. So, more heat is going out from here compared to this boundary, right. Heat is entering from this direction, heat is going out from this maximum 400, then this boundary has more heat going out, this boundary has relatively less heat going out. Now, in steady state, right, once the temperature has finalized, it does not change as a function of time, then basically what is happening is there is no net heat inflow into the system, right. That is what you have specified this for. And if you remember your Gauss's law, if you take A j dot area, now area here will be in this direction, the area element is normal to the surface, is in this direction. The area normal to the surface is in this direction, pointing out, and the area here normal to the surface is in this direction, right. And if you, so A j is of course q vector. If you take q a, yeah, so basically what I am calculating is amount of heat passing through this each of these 4 surfaces, and if you take the correct dot product, you will see that the net amount of heat A j into, I mean, you have to take the sign of delta A as well. If you do it right, you will see that there is no net heat input on the system. The amount of heat coming in is equal to the amount of heat going out, and only under such a condition would you have a steady state. If there was a net heat input into the system, then the temperature of the system would rise, right. But what you have is, there is no del T del time, the time derivative of temperature has been set to 0. That means, you are discussing steady state conditions. Temperature is not varying as a function of time. In such a case, the net heat input into the system has to be 0. Net flux of heat, right. On each boundaries you have a flux, but the system does not gain any net heat. If it gained it, the temperature would rise, and you would see that the boundary conditions have been chosen, or the appropriate boundary conditions would be such that q dot A across the 4 surfaces would be 0, and you can check that for yourself, right. With this background, now let us move and show you the code and figure out how would the temperature profiles look like. Okay. So, the code is called Neumann.Laplace.F90, right, and this is the program Laplace Neumann, and here I specify the lattice sizes, Lx equal to 34 just as is the previous case, and Ly equal to 34 just as the previous case. Now, note I have 4 arrays called A Ly, C Lx and D Lx. So, these are those A, B, C, D which I specify at the boundaries, right. Those are the amount of heat current that you specify at the boundaries, and the rest of it is basically very similar to the previous code, except in my previous case I was specifying the temperature at the boundaries, and I was updating the temperature at only the inside points, not on the boundaries. Here we are updating the temperature at the boundaries as well. And so, you see that there are differences where I am not specifying the temperature on the boundaries, which I did in the previous case. Here the code starts directly. So, old temperature has been set to 0 just as an initial condition. So, the entire lattice has initial temperature, or initial does not mean with respect to time, initial here means at the 0th iteration has been set to 0, right, and dx is 1 and dy has been set to dx. That is when those formulas are valid, and you would see that I am basically updating the values of the temperature at the boundaries here. So, I am updating the boundaries first, because the formula is different, because you will have AJs and BJs sitting here. I have just implemented whatever I wrote in the code here. So, old temperature is the older value of whatever temperature is there, right, which has all been set to 0. But what is non-zero in the first iteration are these values, right. So, here I have set the values of A, So, this is Fortran. So, basically though I am writing A, all the elements in the array are being set to minus 700, all the elements in array B are being set to minus 400 and so on and so forth. So, these are non-zero values. So, these are the values which are non-zero, this and this. At the 0th iteration, all of old temperature has been set to 0 here, but after the first iteration, because you have non-zero values here, you have non-zero values in temp, right. So, this is you have basically, though temp would have been 0 initially, it now has non-zero values, and similarly here for the boundary points, you see that this is basically x remains 1 and the loop is only from the boundary points, but note I have left out the corner points. The corner points, the formula is different, hence they are being updated here, right, where you both in the expression for the temperature update at the corners, you both have C1 and A1, and at a different point you have D and you have A, right, and you have B and you have C. So, the corners are being updated separately and they are basically 1 1, 1 Ly, Lx1 and Lxly, but for all other points in the boundary you have A sitting here, B sitting here. In the other cases you have C sitting here, those are the same implementation of the same formulas which I showed, and you have D sitting here. Once you have updated the boundaries and the corners, what you do is basically update the interior of the lattice, and the interior of the lattice is very simple. So, you go to each lattice point in the interior from 2 equal to Ly minus 1 and 2 equal to Lx minus 1. Write down the expression which you get by solving the finite differences method, which is was also discussed last time. You update all the points, the new temperature, right. Then you check for convergence at each lattice point, right. So, you go to each lattice point and check that the new value of temperature, what is the difference from the old value of temperature to the new value of temperature, right, and if it is above a certain tolerance level, say 0.01 or even if you put 0.001, right. If the difference is more at any point is more than 0.001, then basically you set a dummy variable test equal to 1, and only if test equal to 0 do you exit this number of iterations loop, right. Test is being set to 0 every time. This is the loop over iterations, test is being set to 0. Here you are checking if any of the differences in temperature is above your tolerance level, test is set to 1, then it can't exit the loop, and then you basically old temp is set to temp and you go on doing this, right. Now, what does one do? Well, one compiles new Laplace dot F90 minus O to new Laplace, then you run it, and you see that it takes 4329 iterations, number of iterations for the results to converge to the final temperature distribution. How do we visualize it? Well, you have again the show color just as previously, all the final data is being stored in 10,000. So, initialize dot 10,000, and you can open Octave, which I have already opened, right, and show color. So, this is the temperature distribution, this is along x, this is along y, and that is something which is very fishy. And what is fishy is that the blue color is minus 5000. How can temperature be minus 5000, right? I mean, suppose you are discussing it in Kelvin, you can't have. So, there is something which is fishy, which is not sensible. What is that? we will discuss it. But meanwhile, if you remember, heat was coming in from this direction, and you have a very high red color here showing high temperatures. Heat was going out minus 400, the dT dx, the heat going out was minus 400 here. Correspondingly, you have relatively low temperatures here. There was more heat going out from this direction in along this direction of y compared to this. So, you see that you have a higher value of temperature even here compared to not higher value, but higher distribution. I mean, it is hotter over a larger amount of space here compared to here, because more heat is going out in this direction and this direction compared to this direction. So, the thing seems to make sense, but this temperature range is completely off the mark, it does not make any sense. Maybe we should change the temperature a bit, the amount of heat going in or coming in a bit. So, suppose you decrease the amount of heat current, and let us see what happens. You will see that the problem will remain. Now, you have got to the final value of the temperature distribution in a fewer number of iterations, but if you again plot the data, you have a similar distribution of temperature, but the range of temperature is still minus 100, though it has gone from minus 500 or minus 1000 to 1000. Temperature cannot be negative. What is going wrong? Okay, it is very important to realize this. It is intentionally that I showed you this code. So, what is happening is you have set the temperature arbitrarily to 0, right, as the initial condition. That really does not make much sense, and I have also set it to 1000, right. And if you are talking in Kelvin, setting the temperature arbitrarily, the initial condition if you like, to 0 is pretty arbitrary, and from that all that you have is the amount the heat current, the amount of heat going in and the amount of heat going out. So, all that it cares about is the gradient in temperature, the changes in temperature about this certain arbitrary value of initial temperature scale that you have set, right. And if you set that correctly, you will not have such problems. So, what you have to do is say that somehow you set the temperature at one corner to be 2000, right. I mean, you set your temperature whatever in your right units. Right now, all the units, all the scales are 1, right, but you can, I mean, not necessarily you will be working with a 34 cross 34 lattice. You might be working with a plate of size 0 to 2. And then you need to then discretize the lattice, then you will have finite values of delta x and delta y and so on and so forth. So, putting in units is, suppose at some point you say that at one corner, at corner suppose 1 and 1. So, the left hand bottom corner, you set the temperature to be 2000. So, that every time you in an iteration you change the temperature, but you want the temperature at this corner 1 and 1 to be remain 2000, right, and that is how you implement it. Think about it, how you would implement it. I am intentionally not explaining this part, but suppose you want to maintain the temperature at this point to be 2000, and accordingly shift the temperatures of all the other points. All that you have is the gradients, right, and use the differences in temperature, and now you are saying that one corner shall maintain a temperature whatever 2000, you can choose 1000, does not really matter. And then with respect to this point where you are specifying both the temperature and the gradients, it is like Cauchy, right. What are the temperatures at the other points given the certain boundary conditions where you are specifying the heat coming in and the heat going out, right. Now, if you do that, I compile it again, run it again, and the data is being stored in the same file. You should put it, if you want, you can put it in a different file, and if you plot the data, this is what you get, and this now makes more sense, right. So, under those conditions, if you are maintaining Lx 1 to be temperature 2000, which is here, then the temperature distribution over the rest of the plate. So, here it will be higher than 2000 because you are putting in a certain amount of heat, but less amount of heat is going out from this direction. So, here you have higher values of temperature than 2000, here you have lower values of temperature. So, it would be somewhere here, here you have medium values of temperature, and this is how the temperature distribution would look like given the boundary conditions. Now, of course, you can have put in boundary conditions, so that the amount of heat current is also changing along here. So, right now it is 100 here and 200 here, and incoming heat is 700 and outgoing heat is 400. You can make them more complicated depending upon your real engineering problems or whatever problems. When you are doing a thermal conductivity problem, you can have different boundary conditions, those have to be put in, and you can find out the temperature profile, right. So, this was essentially a discussion of the Dirichlet boundary condition, which we discussed in last class, Neumann boundary condition, which we discussed in today's class, and we touched upon Cauchy boundary condition. But really, you know what, if you are discussing diffusion equation, you would also might want to know that if you set up these boundary conditions at time t equal to 0, how would the temperature profile evolve as a function of time? Del T temperature, del tau, tau being the time. Now, if you have to do that, you can basically put in a suitable finite differences method for del T temperature versus del tau time, but you can do it, but one has to be a bit more careful, because you can use first order finite difference formula, and then one has to look carefully, analyze the stability conditions. The criteria, not always the answers are stable. Or alternatively, you have to basically give an initial conditions, the initial boundary conditions, and then maintain the boundary conditions the rest of the time. So, this is a bit more involved. When you do it, you also have a Laplacian on the right side of the equation, and you have also temperature as a function of time. That would actually need quite some bit of learning, stability conditions, what are the different expressions, what order scheme should you use for writing del T del tau, and that if and when you need it, we hope that with this at least introduction, you can read up the book and learn about it. You might have realized that in this course, we are touching few of the topics, Monte Carlo, Ising model, and random numbers, random number integration. We are doing this in a hands on manner, but if we had to basically do larger number of topics, we wouldn't have so much time to discuss these things in a hands on manner. So, the hope is we are exploring, we are basically giving you an introduction to various kinds of computational techniques and algorithm building. And in the next class, we will be starting molecular dynamics, and with this various exposure to different kinds of thoughts and algorithms, and implementing different kinds of algorithms in the computer whenever you need in the future, right, which will of course very likely to be beyond the scope of this course techniques, you will be able to read up the book and learn from what the algorithm building and implementation and the background physics from the book, right. So, this class is basically the end to this module, and from the next class you will have a different module, and I shall teach you molecular dynamics after a few more lectures which will be given by Prashanjit Ghosh. Thanks.